Welcome to Radiation and Astronomy. As you just saw with history of astronomy, the main reason we studied, the main way we studied was looking at the stars from the radiation sent from our own light that our eyes could pick up. Since then, though, we realized there's different types of radiation given off in space. So we have found that electromagnetic radiation does travel through space untouched. It can travel through space, it can go around things, and it has two properties, electric and magnetic properties. And there's more than one type, more than just light. So it has an electrical field and magnetic field, and they run perpendicular to each other. The homework you're going to do in class, this is a flipped class. So electromagnetic radiation, we'll call it light, but it's also radio waves, TV waves, all that stuff. It travels in waves. It has a crest and a trough. The amplitude is the height of the crest. So that could be like volume is be turned into sound. Wavelength is from crest to crest. The shorter the wavelength, the higher the frequency. That is, the more frequent those crests pass by a certain point at a given time, since all electromagnetic radiation travels at the same speed. So radio waves, television waves, light waves all travel at roughly 300,000 kilometers per second. Wave. So wavelength is the distance, again, from crest to crest. We abbreviate wavelength using the Greek letter lambda. So electrically charged particles give off an electrical field which is stronger the closer you are to it. So when particles vibrate, the electric field changes. This causes the wave. You're getting off electromagnetic waves right now. The heat in your body, where your atoms are moving to give off heat, what we call infrared radiation. So as atoms vibrate, they give off waves. So everything out there that is above 0 Kelvin that's moving gives off electromagnetic radiation. What's called EM radiation. That's a lot easier to say than electromagnetic. All right, there it is again, showing how vibration gives off waves. So magnetic field is associated with every changing electric field. So magnetic fields exert forces on moving electric charges. You can see that when you hold a magnet against a television screen, for instance. But electric fields are perpendicular to the magnetic fields that accompany them. The word perpendicular is big, bold, and red, and the whole sentence underlined. So know that, not underlined, but it's big, bold, and red. They're electromagnetic waves. They look like this. Nice little diagram straight from your textbook. So a wave moves in one direction. The magnetic field is perpendicular to the electric field. Nice little cartoon feature of it, and shows again lambda, wavelength is crest to crest. So the wavelength varies. The reason why all electromagnetic radiation is different is because of the wavelength. Infrared has a much longer wavelength than does blue light, but all EM travels at the same speed, c. You've heard c before, like in E equals mc squared. Here you're going to see c equals lambda f. So speed is always the same. As the wavelength gets shorter, the frequency gets higher. That means more wavelengths pass at a given moment. The frequency is how often the crest wave passes a given point in a given amount of time. Basically how fast it goes at any moment. C, we're going to round up to 300,000 kilometers per second. Makes it really easy to memorize and to use in math. Frequency we measure in hertz, which is cycles per seconds, or wavelengths per second. Your radio waves, you turn to your radio stations, they're that many kilohertz or megahertz. So again, speed of light is wavelength times frequency. As the wavelength increases or gets bigger, the frequency decreases because the wavelengths are further apart, so the frequency of passing that point is less, and vice versa. If the wavelength gets shorter, you get a whole lot of wavelengths passing at a given point in time. So the EM spectrum ranges from the high energy short wave gamma rays. So gamma radiation is the shortest radiation, highest frequency, and because it's got such short radiation, it can do a lot of damage to your DNA and to your body. The low energy AM radio waves, they're such a long wavelength, they don't hurt us, but they do penetrate walls, so we can listen to radio inside of a classroom. We don't want to do that, but we can. So in order from longest to shortest waves, we got AM, short, FM, TV, radar, microwave, infrared, visible, ultraviolet, X-rays, and gamma radiation. You've got to know this, you got to understand this, and a good way to remember this is to make a little saying, such as, oh, we'll get the saying in a second. So here's the electromagnetic spectrum. I like this visual because it shows you that radio waves, their wavelength from crest to crest is like 1,000 meters apart, 10 to the third. Microwave, 100th of a meter, very small. And what that does is gets the water molecules vibrating to heat up food. We use microwaves now in ovens. Infrared is what we give off the heat. Visible light is what our eyes detect. And ultraviolet is even shorter. That's what damages our DNA, causes thymine dimers, which our body fixes and gives us a sunburn. X-rays, very, very, very small. They go through our soft tissue. And gamma rays go through pretty much all of us. Very tiny. And you can see below the frequency, 10 to the 4th hertz for radio waves. That's about 10,000 per second. That's pretty fast, but look at gamma rays, 10 to the 20th, that's 20 zeros. That's a lot of radiation zipping through in a second. Again, here's another nice diagram. You can pause this, look at it. Visible light is from 400 to 700 nanometers. Our eyes detect that. They're designed to detect that electromagnetic radiation, which just blows me away. We can see all these different colors, even though we have basically 3 different color rods: green, blue, and red. Know these in order. So here they are. AM, we just say Ashley should fly to Russia, making it visible under extreme gamma rays. So extreme, you got to emphasize the X. AM, shortwave, FM, television, radar, think of the cop with his radar aimed right at you and getting your speed, microwave, infrared, like there, infrared penetrates through the black bag, you can see the hands. Visible light, which we all see, Roy G. Biv, red, orange, yellow, green, blue, violet, ultraviolet, X-rays, and of course, gamma rays. So diffraction, you've got to understand diffraction. It is the bending of a wave, the deflection of a wave. Waves can be diffracted. So particular light waves are diffracted through a chunk of plastic or glass. As they go through it at slower speed, they get bent and they diffract, causing a prism effect. The colors are separated. Interference is when 2 waves cancel each other out, or they can build on each other. The stars twinkle because they're so far away, their light waves start coming out of phase or in phase. So you get out of phase, in phase, and you get this bright, dim effect. So again, 2 waves can cancel each other out as one is going up, the other one is going down, basically. We'll just keep it super simple. So waves can add to each other. If they're both in phase, then they appear to be twice as high. So radiation does not need a medium to travel through space like sound does. You can scream your head off out in space and be a foot away from someone, they can't hear you because there's not molecules to vibrate. But light, radar, radio, television, all that stuff, it travels through space without a medium. It does not need stuff to pass through. Electrically charged particles exert an electrical force on every other charged particle in the universe. They all affect each other. Here's some facts. 1. Wavelength determines the type of radiation. We already alluded to that earlier. That super long wavelengths are AM radio. Super short, gamma. Everything else in between has different wavelength, all the same speed. Visible light only makes up 400 to 700 nanometers, and our eyes detect that range. There's the frequency of red and violet. So, little artistic rendition. They have basically 4 waves of blue, 4 waves of green, and 4 waves of red. You can see the wavelengths are longer in red, but they travel the same speed. Yes. Which has a higher frequency? The blue. All right, this is a nice picture of our sun in a couple different telescopes. One we used a light telescope. The other one we used the infrared or X-ray. Opacity is the extent to which radiation is blocked by a material it's going through. So light can pass through windows, clear as a bell, yet a window can block infrared or heat. The converse is true with a black piece of plastic. You saw the guy holding a plastic bag over his hand. You can see his hand with an infrared scope, but light does not pass through the black. Our atmosphere is opaque to most. It lets a little bit of gamma radiation and stuff get through, but it pretty much blocks out everything except radio waves. That's why we have big radio telescopes on Earth. Some infrared, a little bit of heat gets through. We have some infrared telescopes high on the mountaintops. Visible light, of course, because we can see visible light. Okay, so those are the 3 biggies that make it through pretty easily through our atmosphere. Everything else is, most of it's blocked. I say most. So water, oxygen, ozone, and carbon dioxide are big in blocking, reflecting, or absorbing a lot of the radiation entering Earth. Basically, they absorb it and shoot it off another direction, so they change the direction of it. Water and oxygen mainly absorb radio waves. Water and carbon dioxide absorb infrared, and we all know it absorbs ultraviolet because they make a big deal about our ozone layer being depleted. And the ozone is very important up in our ionosphere for blocking a lot of the ultraviolet, X-ray, and gamma radiation. And ions, of course, up in the ionosphere, do reflect longer radio waves. So ham operators, the shortwave operators between AM and FM waves, will use that to their advantage, and they'll bounce the radio waves off the ionosphere to talk to people around the world. Matter of fact, if you tune into 8:50 AM at night, you can pick up a Denver station. All objects emit radiation. Here's a picture of an infrared picture of a house used by an insurance company or maybe someone who's selling insulation. They can find the spots which are leaking heat. You can see the windows very red. Red means a lot of heat's lost. Blue, not much heat loss at all. So there they know you can put some insulation around there and save some money. But all objects emit radiation. They're all called a black body. A black body is any object that emits radiation. So what it does is it absorbs it, turns around, and shoots it back out. So it's the same amount of energy it absorbs. Energy is neither created nor destroyed. It's simply transferred. Again, temperature is the measure of the amount of motion of particles. The more motion, the higher the temperature. Think about that when you rub your hands together really fast.